Hello everyone, welcome to the YouTube channel of TriboNet. My name is Manoj. Today, in this video, let us learn about area of contact between stationary surfaces experimented by Bowden and Tabor. Hertz in 1881 worked and established theoretical equations describing elastic deformation and the contact area between curved surfaces under load. The subsequent researchers like Bidwell and Mayer investigated electrical conductance in the contacting materials, with Mayer linking the contact resistance to pressure, though later studies suggested surface contamination affected his results. Finally, Holmes' extensive research from 1922 onwards showed that the contact resistance for clean metals adheres to Holmes' law and arises from spreading resistance due to current constriction in small contact areas. And he concluded that the flat surfaces consist of numerous of small contact points or asperities. Here in this figure, we can see the schematic representation of the flat surfaces with asperity contact. What did the modified derivation by Bowden and Tabor do? When a metal is very soft and subjected to high pressure, the contact area can approach the size of the entire metal surface. In such cases, the spreading or resistance decreases, and according to this condition, where the radius of the contact area small a equals to the radius of the metal surface small r, the spreading resistance becomes zero, and hence the modified equation of this electrical conductance is given by the one below. What are the experimental setup used by the Bowden and Tabor to come to this conclusion? Two crossed cylinders were arranged with their axes at the right angles. The electrical conductance capital A was measured using the current potential method. A known current small I was passed through this contact, and the potential difference small v was measured using the high resistance potentiometer or galvanometer, and the conductance was calculated using A is equals to I by V. The contact surfaces were prepared through the final grinding and polishing of the chemical etching or scraping. Although the surface preparations had a minimal impact on these results, scraping improved reproducibility. Here in this figure, we can see the experimental setup used by Bowden and Tabor. The important results and discussions from these findings were: the metallic nature of the contact. The measured conductance aligns with the metal's specific conductivities, implying the resistance arises mainly from the metal to metal or carbon to carbon contact, not from the oxide layers or the contaminants, which must be extremely thin in the present. What are the load dependent conductance? The conductance varies systematically with the applied load, following a cube root relationship in elastic deformation and a square root in plastic deformation, though distinguishing between the two can be difficult due to the measurement uncertainty. What are the other findings? The effect of surface shape. For a single point contacts like sphere on flat, the conductance is consistent across the varying curvatures, indicating that the contact area and thus the conductance is relatively unaffected by the surface shape as long as the contact is continuous. What about the flat contact surfaces and their limitations? Although flat surfaces have a larger potential contact area, actual conductance only slightly increases, suggesting that the limited intimate contact via multiple discrete points or bridges, making the conductance largely independent of the apparent contact area. And what is the estimating real contact area? For the flat contacts, the conductance alone can't accurately determine the real contact area because it depends on the number of the size of the contact bridges. Fewer bridges imply larger individual contact areas, but at least 3 contact points are needed for the stability. So finally, what are the conclusions from these findings? It is clear that for flat surfaces, the real contact area, even under the significant loads, is only a small fraction of the apparent area. The flat surfaces are kept apart by small surface irregularities that creates a metallic bridges under applied pressure. These bridges either flow or their number of increases until their total cross section is largely enough to support the applied load. In general, the load conductance curve for a flat contact surfaces to be steeper than for the curved surfaces. However, it is challenging to propose a satisfactory quantitative hypothesis to fully explain this behavior. This is the reference for this information. In this video, we understood what are the history or the introduction to the area of contact between the stationary surfaces, and how did the Bowden and Tabor modified this derivation and their experimental conditions and the findings of the experimental conditions with conclusion. Thank you for watching this video, and to get more details on the topics related to tribology, follow us on our social media pages on Instagram, Facebook, LinkedIn, and do not forget to subscribe to our YouTube channel TriboNet. Also visit our website on www.tribonet.org.